Imagine you're a researcher at a frontier AI lab, and your CEO has just announced that human-level artificial general intelligence is no longer a distant dream, but a concrete target for the next decade. A reasonable next question follows almost immediately. What happens after that? If we actually build a system as cognitively capable as a smart human, does progress stop there, or does it keep going? And if it keeps going, where exactly is it headed? That question, the trajectory from artificial general intelligence, or AGI, to artificial superintelligence, or ASI, is what this report from a large team at Google DeepMind sets out to map. The motivation here is not to deliver a new algorithm or benchmark result. It is to provide a conceptual framework for thinking carefully about a transition that, until recently, lived mostly in science fiction and philosophy. The authors argue that the popular image of AGI as a single dramatic threshold, a moment where everything changes at once, may be misleading. A more accurate picture might be a continuum of machine intelligence, where AGI is just one notable point along a longer road, and where the societal transformation comes not as one earthquake, but as a sustained sequence of breakthroughs across science and technology. To anchor this continuum, the report leans on a theoretical endpoint that is actually well understood mathematically, called universal AI. The classic formalization here is something called AXI, developed by Marcus Hutter, who is one of the co-authors. The intuition behind AXI is elegant. Imagine an agent that at every step considers every possible computer program that could explain the data it has seen so far, weights simpler programs more heavily following a formal version of Occam's razor, and then picks the action that maximizes expected future reward across all those weighted hypotheses. It is provably optimal in a precise sense, but also provably uncomputable, meaning no real machine can actually run it. Think of it as the thermodynamic limit of intelligence, useful as a North Star even though you can never reach it. Universal AI gives the report a formal ceiling, and the central question becomes how the path from human-level AGI climbs toward that ceiling. Before mapping pathways, the authors spend time characterizing what ASI actually means. Rather than defining it as a single number on an IQ scale, they describe it intuitively as a system more cognitively capable than large organizations of humans working together. That framing matters because it sidesteps narrow definitions and instead points at the kinds of problems an ASI could solve, things that today require coordinated efforts of thousands of scientists, engineers, and institutions. They distinguish capabilities along axes like breadth of domains, depth within each domain, speed of cognition, and the ability to coordinate across many parallel instances of itself. With that target in mind, the report lays out 4 candidate pathways from AGI to ASI. The first is straightforward scaling, the hypothesis that whatever recipe gets us to AGI, more compute, more data, more parameters, and better engineering will push it further into superintelligent territory. The second pathway is a paradigm shift, where some new architectural or algorithmic insight, perhaps something as different from transformers as transformers were from recurrent networks, unlocks qualitatively new capabilities. The third is recursive self-improvement, the classic idea where an AGI becomes capable enough to do AI research itself, designing its successor, which then designs its own successor, creating a feedback loop. The fourth, which is perhaps the most underappreciated, is emergence from large-scale multi-agent collectives, where superintelligence arises not from a single monolithic model, but from many AGI-level agents interacting, specializing, and coordinating, much like human civilization itself produces collective intelligence far beyond any individual. For each pathway, the report carefully discusses frictions and bottlenecks that could slow or halt progress. Scaling could hit walls in compute availability, energy, data exhaustion, or diminishing returns on capability per unit of resource. Paradigm shifts depend on research breakthroughs that are inherently unpredictable. Recursive self-improvement faces the question of whether AI research is actually a domain where intelligence translates linearly into faster progress, or whether it bottlenecks on physical experiments, real-world feedback loops, and slow empirical validation. Multi-agent collectives raise coordination problems, communication bottlenecks, and the question of whether collective intelligence actually scales with the number of agents or saturates. Because this is a position and framework paper rather than an empirical study, there are no benchmark numbers or training curves to report. Instead, the contribution is structural. It gives researchers and policymakers a shared vocabulary and a set of concrete open questions. Which bottlenecks are likely to bind hardest? How would we measure progress along the AGI to ASI continuum? What evidence would let us distinguish between the four pathways playing out in practice? The authors are explicit that uncertainty is enormous, and that responsible forecasting requires treating these as research questions rather than settled predictions. The limitations of the report are also worth naming honestly. Because it operates at a conceptual level, many of its claims are hard to falsify in the short term. The universal AI grounding, while mathematically clean, may have limited bearing on what real systems actually do, since AIX's optimality relies on assumptions like infinite compute and a well-defined reward signal that real deployments do not satisfy. And the framing of pathways is necessarily a simplification. In practice, scaling, paradigm shifts, recursion, and multi-agent dynamics will likely interact in messy ways rather than playing out as cleanly separable scenarios. Still, the report's central message, that we should prepare for a sequence of transformative changes rather than a single threshold event, is a useful reframing for anyone planning research agendas, policy, or product roadmaps in the coming decade. Now let's walk through some questions you might have after hearing all of this. First, why bring up universal AI and AXI at all if it is uncomputable and not what real systems look like? The reason is that having a formal endpoint, even an unreachable one, lets you reason about direction and limits. It is similar to how physicists use idealized limits like absolute zero or the speed of light to bound and structure their thinking, even though no real system actually sits at those limits. Without such an anchor, discussions of superintelligence tend to drift into pure speculation. Second, why is the multi-agent collective pathway interesting if it sounds like just running many copies of AGI in parallel? The interesting part is that collective intelligence is not simply additive. Human civilization is dramatically more capable than any individual human, not because we copied one person a billion times, but because specialization, communication, institutions, and accumulated culture produce emergent capabilities. An ASI emerging from interacting AGI agents could similarly exhibit capabilities that no single agent possesses, which makes it a qualitatively different path than scaling one model. Third, what would actually count as evidence that recursive self-improvement is happening? The key signal would be a measurable acceleration in the rate of AI research progress that is attributable to AI contributions themselves, not just AI tools assisting humans. You would want to see things like AI systems proposing novel architectures that outperform human-designed ones, or autonomously running research programs that compress months of human work into days, with the gains compounding across generations. Without compounding, it is just useful automation, not recursion. For large-scale recommendation systems serving hundreds of millions of users, the framework in this report suggests some concrete shifts in how to think about the future. The multi-agent collective pathway is particularly relevant because modern recommendation stacks are already moving toward ensembles of specialized models, retrieval agents, ranking agents, and increasingly LLM-based reasoners that negotiate over what to surface. If collective intelligence scales the way the authors hypothesize, the right architectural bet may be less about training one giant foundation model for recommendations and more about designing the coordination protocols, communication interfaces, and shared memory structures that let many specialized agents combine into something more capable than any individual component. More practically, the report's emphasis on frictions and bottlenecks maps directly onto production concerns. Real-time serving latency, candidate retrieval at billion-item scale, and the feedback loops between recommendations and user behavior are all places where raw model capability hits hard physical and economic limits. The lesson is that even as upstream model capabilities accelerate, the value in recommendation systems will increasingly come from the systems engineering around them, the orchestration, the evaluation infrastructure, and the alignment of agent objectives with long-term user welfare, rather than from any single capability jump in the underlying model.